Just repost them in chat. Yeah, I'll do that.
Brilliant. I'm juggling several files here, so that would help reduce confusion.
Right.
Tom, you look the same.
What's that? Oh, hi, Roger. Yeah, we've not met for a while, eh?
Exactly.
I can't see you, though. That's sneaky.
Okay, everything's being recorded. The live stream is running, and so we're ready to start. And, Dominic's ready, and Tom's ready.
I'm ready.
Dominic?
Yep. Are you ready to share your screen, Tom?
Yes. Host disabled participant screen sharing.
Does Tom need to be a co-host?
I am now. Okay. So I think I can just share the whole thing. Oh, I don't know why we're right through that. Sorry about this. Ah. Why that happened.
We can leave now.
Hope you read all that.
Yeah.
Okay, so for our second talk today, we're pleased to have Tom Bridgeland from Sheffield, who's going to give the first of 3 lectures on from Donaldson-Thomas invariants to hyperKähler structures. And we'd encourage you to mute yourself if you're not Tom.
Okay, well, thank you very much. I'd like to very much thank the organisers for all the hard work they've put into this organising this event. It's a real pleasure.
Tom, you're muted.
Tom, you're muted.
How are we doing now? Good.
Okay.
Okay, start again. Thank you very much to the organisers for all the hard work they've put into this. So, and thank you also to Brent for that beautiful talk we've just heard. I'm going to try and resist the temptation to relate everything I say to what he just said, because that will confuse me and probably everyone else. But I sort of learned a lot from that talk, and I want to think about it more, but now's not the time. So, so what's this all about? So this started off a long time ago, trying to understand one of Dominic's papers. That's often the case for my mathematics. And in this case, what we were trying to understand was how to encode DT invariants in some kind of geometric structure. So let me say, I mean, the most general framework for studying Donaldson-Thomas invariants, and I would sort of argue the most natural framework, is the setting is the space of stability conditions on some CY3 triangulated category. Okay, so that may seem quite abstract. Hopefully I will explain this as we go along, but that's in some sense, that's the most sort of natural general context for studying these things. And so the hope was that so this space of stability conditions, it's always a complex manifold. And the hope was that somehow the DT invariants could be encoded in some kind of geometric structure on that space. So, you know, very much analogous to the way that genus 0 Gromov-Witten invariants are encoded in a Frobenius structure. Okay, so we wanted to find some other structure which encoded DT invariants. And I think that we now understand what that structure is. So in recent joint work with Ian Strawn, we explained that it's naturally a complex hyperKähler structure on the total space of the tangent bundle of the stability manifold. So I'm going to try to explain in these lectures why that should be the answer. And I suppose the hope is that people who actually are used to doing things like hyperKähler geometry may have some interesting perspectives on what's going on here. And the key idea really is that you should think of the DT invariants as defining some kinds of Stokes data for some isomonodromic family of connections. So I'm going to try to explain that in this lecture. So, but the point is that these connections are not taking values in some group of matrices like the ones Brent was talking about. You know, so his Stokes factors were just kind of n by n matrices. The relevant group here is not GLN, it's some group of diffeomorphisms, or rather symplectomorphisms, of some fixed space, which is in fact a a copy of C star to the n. Okay, so that's somehow the key idea here, is that you're taking some classical story about Stokes data, but you're changing the group from GLN to some infinite dimensional group of symplectomorphisms. Okay, and that connects, I believe, with some much broader subject of resurgence in quantum field theory, which I'm not at all an expert in, but which I'm looking forward to learning about in this event. Okay, so how do you actually get your hands on this hyperKähler structure starting from the DT invariants? You have to do something quite difficult. You have to solve a class of Riemann-Hilbert problems, which I will maybe mention today, but certainly those will appear later in the course. And this is extremely closely related to work of Gaiotto, Moore, and Knightsky from a decade ago. So, I mean, an uncharitable physicist would probably just say it's the same. Well, it's certainly, you could say that it's taken me certainly a long time to fully understand what's going on in their papers. But strictly speaking, it's not, the story I'm describing is not quite the same as what they were doing. It's something that physicists would call the conformal limit. Okay. And exactly as with Gaiotto, Moore, and Knightsky, and this is something certainly that we learned from them, along with many other things, there is a large class of examples of this story where, I maybe should have emphasized before, for us, the story, the kind of data that tells you which story you're telling is this triangulated category. That's the starting data. And so these examples are obtained by taking a particular Fukaya category of a Calabi-Yau threefold, a non-compact Calabi-Yau threefold, which is fibered over some Riemann surface, given locally by an equation like this. And we'll hear particularly about these examples in Ivan's talk. But they relate to a lot of rich mathematics. So in physical terms, these are theories of class S with gauge group SU2. But in mathematical terms, they relate to trajectory structures of quadratic differentials, exact WKB analysis, and the geometry of the Hitchin system. Okay, so hopefully those examples will crop up later in the course. I should say that some of this, you know, I was delighted to give 3 talks on this topic, but it's still somewhat speculative, some of this. In particular, I would like to be able to compute a few more general examples to know that everything is exactly as I expect it to work, expect it to be. So, so there's still definitely quite a lot of work still to do, and there's also lots of interesting questions and unsolved problems in this area. Okay, so the plan of the talks is this is going to be mostly background. It's going to be on stability conditions, DT invariants, and the wall crossing formula. And then I will also try to relate that to Stokes data. And hopefully by the end of the talk, we'll understand why DT invariants should be thought of as Stokes data. And I should say that I've given this talk this sort of talk several times, quite a few times. So please, if you've seen it before, I've posted the notes on the chat, and have a quick look through. If you don't want to hear this stuff again, then please skip it and come to the second talk. But I'm going to try to explain it for those who've not heard about this before. And then in the second talk, I will talk about this geometry that we're expecting to find on stability space. So this will be something about these complex hyperKähler manifolds, their twistor spaces, and I'll try and discuss this class of examples relating to Hitchin systems and theories of class S. And then in the final talk, I will try and discuss these Riemann-Hilbert problems, how you solve them in some simple examples, and you get some kind of things that may be of mild interest to some physicists. So for example, this you get a non-perturbative topological string partition function for the resolved conifold. So some particular analytic function whose asymptotic expansion agrees with the genus expansion of Gromov-Witten theory for that space. Anyway, so we'll come back to that. So this is the first lecture, and as I say, if you've heard this before, please feel free to skip. So let's start with a bit of a recap on stability conditions. So I'm going to start, as I say, the sort of starting data for us is always a triangulated category. So the basic examples of those things that people are familiar with are the derived category of coherent sheaves or the Fukaya category. But you also can define them algebraically using quivers and so on. And I'm going to make this simplifying assumption. It's not very important that the Grothendieck group is finite rank. It's just free of finite rank. It's kind of a convenient assumption. If it's not true, that all that happens is that you take a map from your Grothendieck group to some fixed lattice of this form, but then you have to carry around that data, and it's just easier to make this assumption, which will apply in most of the examples we're going to consider. So then there is this space of stability conditions, and I will give you some examples in a second, but it parameterizes pairs. It parameterizes stability conditions. And what is a stability condition? Well, it's a pair consisting of some group homomorphism, so some linear map on this lattice into C, and some full subcategory of semi-stable objects. So I should say this group homomorphism is called the central charge. And to give a full subcategory, that's the same as just giving a subset of the objects of your category. So you're just picking out some class of semi-stable objects, and this class is R-graded. All it means is that a semi-stable has a particular phase living in the real numbers associated with it. Okay, and together these things have to satisfy some axioms, which I'm not going to go into here. So there's 4 or 5 axioms, quite simple things. And the surprising thing really is that, okay, so you fix your category, and then you consider the set of all stability conditions on that category. So I call that stability space. And the interesting thing is that it has a nice topology on it. And in fact, it becomes a complex manifold, because there is this what happened there? Sorry. Because there is this forgetful map, which takes a stability condition and just remembers the central charge, forgets the kind of difficult stuff of this full subcategory and just remembers the central charge. And that map is a local homeomorphism. So you can just, transfer the complex manifold structure back from this vector space. The set of possible central charges obviously lives in a vector space, and you can just pull that back. So, the intuition of the slogan of this result is that if you deform the central charge, then there is a unique way of deforming this subcategory of semi-stable objects so that the axioms are still satisfied. Okay. And of course, another way of saying it is that if I take a basis for my lattice gamma, then you get local coordinates by taking the central charges of these things. of these lattice elements. Okay, so what are the examples? Well, this is just a heuristic example, but it's somehow where it all started. So imagine you take some compact Calabi-Yau threefold. So it has a complex structure and a Kähler form, Kähler class, and you think about the hyperKähler category of this threefold with that symplectic form. So that doesn't depend upon the complex structure at all, but what you expect is that that complex structure defines some extra data, and precisely it defines a stability condition on this category. And in this stability condition, so I'm just naively thinking about the hyperKähler category, the objects being Lagrangians. So the central charge of a Lagrangian you get by integrating the holomorphic threeform against this Lagrangian. And the category of semi-stables is just the subcategory of special Lagrangians inside there. So so this is this is a very difficult result to try and prove, I believe. I mean, I'm not really even qualified to understand how difficult it is, but certainly it's not known in this form. This is a heuristic example. So again, what you expect really is that the space of complex structures on X should embed in this space of stability conditions. Or more precisely, what you should say is that this space of stability conditions always carries an action of the group of symmetries of the category, the group of triangulated autoequivalences, as they're called. And you shouldn't just think about a complex structure, because you also need to choose a holomorphic threeform to define this central charge. So what you expect is that if you consider the space parameterizing complex structures on X together with a choice of non-zero holomorphic threeform, then that should embed in this quotient, stab mod aut, as some Lagrangian submanifold. Okay, so that's somehow the expected picture. And this is kind of a common thing that happens with these stability spaces, and it's an interesting thing that often you get some relation with moduli spaces that appear in some physical theory, so some moduli space of vacua or something. But they're always these kind of half-dimensional spaces like we saw here, because typically in the physical theory, the central charges are not free to vary, arbitrarily. They satisfy some kind of special Kähler geometry relations, so that anyway, basically the set of possible central charges is some Lagrangian submanifold inside the full vector space. So that's going to be something that will come up again. And something that I'm interested in is how to see these half-dimensional subspaces of the space of stability condition. It's not at all clear from the kind of the categorical setup. And just because these were rather heuristic examples, I should say that there are some rigorous results on the other side of the mirror. So very recently, Chunyi Li constructed open subsets in the space of stability conditions when you take D to be the bounded derived category of coherent sheaves on the quintic threefold. Okay, so a rather inspiring result. Okay, any questions? So another example, which I think is nice to briefly review, this is the one that Ivan will be talking about later. So this is for non-compact Calabi-Yau threefolds. And the advantage is that we have a full description of the space of stability conditions. So these categories depend on some genus and a collection of pole orders, MIs. And just for simplicity, I'm going to assume that those are all greater than or equal to 3. Then there is some CY3 triangulated category. And if we look at this space stab mod aut, then we can get a complete description of it as a space of quadratic differentials. So this space parameterizes pairs consisting of some compact Riemann surface of genus G and some meromorphic quadratic differential on it, having these fixed pole orders Mi and simple zeros. Okay, so yeah, so you shouldn't think of these spaces as being impossibly abstract, right? I mean, this space of quadratic differentials is a perfectly, nice space, and for particular values of g and m, you can just write it down explicitly. And so I think in physics language, this corresponds to studying theories of class S with gauge group SU2. And again, they don't quite see this. They don't really get this whole space. They would prefer to consider the space where you fix the surface S and just consider quadratic differentials on a fixed Riemann surface. Okay, whereas here we're varying both pieces of data. And so I think if you fix
Tom, could I comment, if I may?
Sure.
Greg, no, the physicists do consider varying S. Those are called the coupling constants of the theory. S as a Riemann surface. Now, that complex structure on S has a very definite physical interpretation. It determines what are called the coupling constants of the theory. Okay. I can explain more later.
Thank you, Greg, for that comment. That's, yeah, thank you. That's very worthwhile to say that. I mean, I think one can still appreciate that fixing S defines some nice, interesting subspace in this full space of quadratic differentials. And it's not at all obvious what that submanifold is if you only know the central charge coordinates. So if you only know these, which are essentially the periods of this quadratic differential, if you only know that, it's not at all clear what the locus is corresponding to a fixed Riemann surface S. And that's somehow analogous to that previous problem of the moduli of complex structures embedding in the space of stability conditions. But yes, thank you. I need to, I'll look forward to hearing more about that. So, and where did we get this category from? So in this case, this is, I mean, we actually constructed it using quivers drawn on the surface, but you can, as Ivan will probably explain, you can think of this as being embedded in the Fukaya category of some non-compact threefold, which is defined locally by this equation. So it's fibered over the surface S, and it's cut out by this equation locally. And the point is somehow that as a symplectic manifold, it doesn't matter which Q you put here. So the category doesn't depend on Q, but the stability condition does. Hang on, I'll just get a drink. Okay. So let me now introduce very briefly DT invariants. I'm really not going to say much about this. So for this, so far we've, in theory, been talking about an arbitrary triangulated category. So we really need the CY3 property at this point, which is this duality property here. So HOMs in one direction look like HOMs in the other direction with a shift and a dual. And this basically comes from Serre duality on a, in the case when D is the derived category of coherent sheaves, this is Serre duality. And then given a stability condition, you hope to be able to define DT invariants. And these are, this is a long story and these are complicated things to define. They were, defined by Richard in his thesis, and then work of Joyce and Kontsevich and Sogelman defined them in greater generality. I mean, you can think, so very first approximation, you can think of them as you take the moduli space of stable, semi-stable objects of some class gamma in your Grothendieck group. And that should be some nice moduli space, and you take its Euler characteristic. So in particular, if this moduli space is particularly nice, if it's smooth and there are no strictly semi-stables, then I guess this is actually the right answer up to sign. But that's almost never the case. So, that's a bit of a cheat. And in general, these things are rational numbers. And I should say there are some equivalent invariants called, which are really the BPS invariants coming up in physics. And they're defined by this kind of multiple cover relation. Well, it looks like a multiple cover formula in Gromov-Fritten theory. I guess it doesn't really have anything to do with multiple covers in this context. and both these classes, both these types of invariants are called DT invariants, but you should distinguish them a little bit. So in my notation, this is DT and the other one is omega. Okay. And then what I'm wanting to talk about first is the wall crossing formula, which is somehow telling you how these DT invariants change as you change the stability condition. Okay. So the point is that if you fix the class gamma, then what happens is that your space of stability conditions, which is this complex manifold, is cut up into chambers by some real codimension 1 walls, and the DT invariants are fixed in each chamber, DT of this gamma, for this fixed class. The DT invariant is the same as you move around in the chamber, but when you cross one of these walls, the number will change. And we want to understand that process. So to do that, I need to introduce a little bit of extra data. So, which is just some standard stuff. So I had this lattice gamma. So I want to consider the torus, who's the algebraic torus, whose character lattice is gamma. Okay, so it's a copy of C star to the n, and functions on it are linear combinations of characters. And I denote the character corresponding to a lattice element gamma by x gamma. And then there is this canonical form on gamma, which is called the Euler form. It's gotten by taking the alternating sum of the X groups, as I would call them really, between two objects. That form descends to the Grothendieck group and defines this thing, the Euler form, and it's the CY3 condition tells you that thing is skew symmetric. And that gives you that form will therefore give you some Poisson structure on an invariant Poisson structure on this torus T, which in terms of characters is just given by this form. Okay, so this is just some kind of basic data associated to the category. So for example, if you were thinking about the Fukaya category of a CY3 fold, really gamma is H lower 3. So it's homology, third homology with integer coefficients. This form is just the intersection form on H lower 3. Okay, so and this torus is really H upper 3 with coefficients in C star. Okay. And this intersection form gives you a Poisson structure on it. And then we need to think about the group of automorphisms of this torus. So by the way, whenever I say automorphism, it's maybe a little bit sloppy. I don't mean automorphism preserving the group structure, okay? Forget about the group structure. Just think about this as a copy of C star to the n, and I want to think about automorphisms of it as a complex manifold, preserving this Poisson structure. Okay, so Poisson automorphisms. So that's an infinite dimensional group, and much of what I say is going to have a little, it's going to be a little bit heuristic because that's a sort of a scary group. But anyway, let's think first about the Lie algebra. So that's going to be vector fields on T and whose flows preserve the Poisson structure. Okay, so I mean, again, I should really be considering maybe all holomorphic vector fields or something, but just this is slightly a heuristic discussion for now. Let's think about just the algebraic ones. So there is some, I can think about a root decomposition of this Lie algebra with two pieces. So the first piece, H, is going to be the Cartan. So this consists of just the invariant vector fields on T. So the ones that are just translation invariant or whatever the word would be, multiplication invariant, just the, the constant ones. So as ever, those can be identified with the tangent bundle to this, the tangent space of this torus at the identity. Okay, and since the torus was Homs from gamma to C star, that's just going to be Homs from gamma to C. Okay, so that's a commutative subalgebra, and so I think of that as being like the Cartan. And so you know, always I'm thinking a little bit about the analogy with GLN, in which case this would be diagonal matrices and this would be off diagonal matrices. You see, so that's where that funny OD is coming from. It means off diagonal. But in this case, what this subalgebra really is Hamiltonian vector fields. Okay, and so you should think of that, well, that is the Poisson algebra of non-constant functions on the torus. Okay, so it's precisely what we had before. It's linear combinations of non-trivial characters. Okay, and so, you know, the bracket of the corresponding Hamiltonian vector fields is just this Poisson bracket of the functions. So really this part of the algebra of vector fields is just the Poisson algebra of non-constant functions. Okay, so that's, you know, that's the Lie algebra that is going to come up in this story. Okay, so, you know, as I said before, part of the key point about this is that we're going to take a rather classical story about differential equations with values in matrices, and we're going to turn it into a different story about where we're just going to replace the matrices by elements of this Lie algebra or the associated Lie group. Okay. So one other thing is that what should I think of when someone gives me a stability condition? What picture should I have in my head? So the first picture I have in my head is this thing called a ray diagram. So it's a very simple thing. It's just it's a diagram in the complex plane, and it's just the central charges of all the stable objects and the rays that go through them, basically. So yeah, so you have, I mean, what else do you have with a stability condition? You have a central charge, and you have a collection of you know, a subcategory or a collection of stable and semi-stable objects. So the thing to do is, well, the only interesting diagram you could draw really is look at the central charges of all these stable objects. So in this example, I'm taking the case of, it doesn't really matter, but this example is the derived category of coherent sheaves on the resolved conifold. So that's a threefold which just has a single rational curve C, and so the stable objects in this case for this stability condition are all the different line bundles on that rational curve. So O of -1, O of 1, and so on. And then also all the skyscraper sheaves of points. Okay, so I guess we would call these D2 branes and D0 branes. And then you also have the associated shifts. So this is the derived category. So its objects are complexes of sheaves. And so I can take a sheaf and put it in degree -1 or -2 or whatever. And when I shift it by 1, the associated class in the Grothendieck group changes sign. So that means the central charge goes to the negative. Okay, so if I shift this stable object by 1, I get another stable object. Its phase shifts by 1, and its central charge changes sign. If I shift it again, I get back on top of this one. So there is also OX shifted by 2 here, and OX shifted by 4, and so on, but I haven't put those in. Okay, so that's this ray diagram. And then in the case when you are talking about a Calabi-Yau 3 category, somehow DT theory enables you to associate to each of these rays an element of a group, that group being automorphisms of this torus. So that's really what happens. We sort of get to label each ray in this diagram by an element of a group. Okay, so what are those automorphisms? So this looks a little bit scary, but it's, well, I suppose it is a little bit scary, and it's also a little bit unrigorous. So so let's take a ray in that diagram just shown you, and I want to associate it to an automorphism, a Poisson automorphism of this torus T. So what I'm writing here is what this automorphism does on functions when I pull back functions by this automorphism, or even characters. Okay, so I take a character on my torus, and I pull it back or compose it with this automorphism, what do I get? So, I mean, basically, you should consider, you should only be interested in classes which live on this given ray. So remember that diagram in the complex numbers, every object of my category gets mapped into that diagram by the central charge. And I'm only interested in those classes in the Grothendieck group which get mapped onto that ray. And then I take the associated DT invariant multiplied by the character. So I take this sum of DT invariants, or basically, sorry, this is a generating function for DT invariants on that ray. And then the automorphism is just the time one Hamiltonian flow of that function. Okay, we have a Poisson structure on my torus, so it makes sense to take a time one Hamiltonian flow. Of course, algebraically, what that means is we take Poisson bracket with this function. That's a derivation of the ring of functions, and I exponentiate it, I get an automorphism of the ring of functions. And if you do this, if you think about that multi-cover style formula we had before relating the dt and the omega, then it's a simple calculation to show that you can rewrite this in this form here, which is very familiar in DT theory and in the physics literature. Okay, so there are various problems with this formula. I mean, basically this, well, yeah. I mean, on the one hand, this could be an infinite sum, so it might not even define a function on the torus. And on the other hand, you can't take time one Hamiltonian flow of an arbitrary Hamiltonian. You know, that flow might not converge. And you know, on this side, again, this product might be infinite, so you might worry about that. And even if only with finitely many of even if this product is finite, this is not actually an automorphism of the torus. It's a birational automorphism, because you know some of these numbers here may be negative, so this will be ill-defined when x equals 1. But anyway, I'm not going to worry about these issues too much. So let me just say that there are various ways to deal with them. And it sort of depends what you're trying to do, to which one is the best thing to think about. One thing is, instead of considering automorphisms of this ring of functions on the torus, which is some kind of Laurent polynomial, the algebra of Laurent polynomials, you can replace that with formal power series, and then everything here will converge. Or you might work with birational automorphisms in some cases, or in general you might need to work with automorphisms which are only defined on some analytic open subsets. So for example, you know, you might want to assume that all these x gammas have modulus less than 1. Anyway, it kind of gets complicated, but let's not think about that. And another thing I'm sort of ignoring here is really it's not quite the torus T that one should consider. It's some torsor over it, which just, when you unravel that, it just has the effect of introducing some signs into this formula, which I'm really just going to ignore for now. Okay, so there is some automorphisms associated to these rays, and then here is the wall crossing formula. It says that basically, if you take the clockwise product of these automorphisms associated to a bunch of rays, then that should remain constant as you move around in stability space. Okay, so you choose some, yeah. So remember, this is what I'm drawing here is the ray diagram we had before, and remember that these rays are sort of spans of the central charges of objects. So as you move around in stability space, that's the same as moving the central charge. And when you do that, these rays can collide and separate. So they can cross each other. And that's when the wall crossing happens. That's when the semi-stables change, when two of these rays align. And so what you do is, you know, you're only interested in understanding the wall crossing near some point in stability space. So you take your ray diagram at that point, you draw these blue lines so that the red lines aren't too near them. And then you move just a little bit near that point in stability space, these red lines will move around, but hopefully they won't cross these blue lines. And as long as they don't, the idea is that this product should be constant. Okay, so the individual factors appearing in this will change, but the product is constant. And basically it's just because this group is non-commutative. So if I change the order by crossing these rays, then the individual factors have to change to make the answer the same somehow. So it's some, you know, so then if you unravel all that in terms of the DT invariants themselves, obviously that's some quite complicated change in the DT invariants. But this is the kind of correct way of explaining what's happening. Okay. And you can make perfectly good rigorous sense of this if you follow that that idea of replacing Laurent polynomials with power series. Okay. So let's just do a simple example of this. So this is the case of the A2 quiver. So here, the lattice is just of rank 2 with a single, this is the that form, the skew-symmetric form is determined by this. And functions on the torus are just Laurent polynomials in 2 variables. And then there are basically 2 chambers in stability space. In one of these chambers, the only stable objects are the vertex simple, so the simple representations of the A2 quiver. So you have, and they have classes gamma 1 and gamma 2. So you only have 2 non-zero BPS invariants, which are these ones. I mean, strictly speaking, you also have omega minus gamma 1 and omega minus gamma 2, but let's, I'm not, so yeah. Okay, so you have these 2 non-zero BPS invariants. And then when you cross the wall and go into a different part of stability space, it's different precisely because the order of these 2 things, the order of the phases of these 2 things is swapped. So on the wall, all these 3 things lined up. On this, in this other chamber, what happens is that you have 3 stable objects. So the representation of dimension vector 1, 1 is also stable. So that's the extension of these 2 things. And so you now have 3 non-zero BPS invariants, and that's what happens on the other side of the wall. And the wall crossing formula says, is an identity like this. So you take the product of something on this ray and something on this ray equals the product of things on these 3 rays. And what are you taking on each of those rays? You're taking some birational automorphism of the torus, which on characters is given by this. So yeah, it's some specific birational automorphism of C star squared. So you've got a combination of 2 of those things is a combination of 3 of them. Okay, and that's the simplest example of this wall crossing formula. Okay, so what I just explained is the most general feature of DT invariance. I mean, it's, you know, depending on what context you're working with, there are many different things about DT invariance which are interesting. But this wall crossing formula is something extremely general that happens whenever you have a CY3 triangulated categories for which you can define the DT invariance. Okay, so, you know, it's telling you something very basic about DT invariance. And now I want to explain that this, you know, it's entirely analogous to something that happens in the theory of Stokes data. So I need to give you some introduction to Stokes data. So we're first going to consider this in the case of a finite dimensional group, GLN. And that's, you know, here's the associated Lie algebra, and here's the standard root decomposition. So H is diagonal matrices, this is off-diagonal matrices, and this is the decomposition into elementary matrices. And of course, later, we're going to replace these with those infinite dimensional objects that we were talking about before, where the Lie algebra is Poisson vector fields on T, and the group is Poisson automorphisms of T. And there is this analogous root decomposition, which we discussed, where H is somehow now invariant vector fields, and this off-diagonal part is Hamiltonian vector fields, or rather functions, which should be interpreted as Hamiltonian vector fields. Okay, and then we consider an irregular, a differential equation for functions from C star into GLN, into our group, of this form. Okay. So this is of the form that Brent considered in his talk. And the point about this, so I should say that, you know, this equation depends on these two bits of data. So U is going to be some diagonal matrix, and I assume that it has distinct eigenvalues, as exactly as in Brent's talk. And for simplicity, I'm going to take V to be off diagonal, so it has zeros on the diagonal. So these are two constant matrices, and then I write down this matrix differential equation. Okay. And my parameter in the complex numbers, for some reason, is epsilon. It's not small or anything, it's just a parameter on C. Okay. And so where did this come from? It's just that this is basically the simplest example of an equation with an irregular singularity. Okay, so it's irregular because it has a pole of order 2 here. Okay, and the phenomena I'm going to discuss are universal, so they would happen for any equation with irregular singularities. But this is the simplest example, so it's the best place to see them, and it's also the correct setting for the analogy I want to make. Okay, and you should notice that if I put v equals 0 here, I can just solve this equation. The solution is e to the minus u over epsilon. So you see that we have solutions with exponential growth or decay as epsilon goes to 0, and depending on which direction I approach 0 from. Okay. So now, again, as in Brent's talk, I'm just going to define the Stokes rays of this equation to be the rays spanned by the differences in the eigenvalues of the leading term u. Okay. So notice that another way of saying this is that U is a diagonal matrix. It lives in the Cartan, whereas there are we have the set of roots which live in the dual of the Cartan. So we can combine those, and of course that just gives me the collection of things ui minus uj. But this is the kind of the right Lie theoretic way of saying this. And I mean, yeah, maybe I just skip this comment for now. And so the main result, the main existence result you need is that there are actually canonical solutions to this equation in half planes. Okay, so these red arrows are those Stokes rays that I just defined, spanned by the differences of the eigenvalues. And if I take some half planes centered on one of those, then there is a unique solution in that half plane, which has the asymptotics e to the minus u over epsilon. Okay, which, you know, we should understand where that came from. That was the solution in the simplest case when v equals 0. Okay, so once you fix the asymptotics like that, then there is some unique solution in the half plane. And then what the Stokes data is all about is comparing those solutions for different half planes. Okay, so if you vary this blue line, this blue ray, then you can just analytically continue this solution. But if this blue ray crosses one of the Stokes rays, then the canonical solution changes. Okay, and the way it changes is controlled by this Stokes factor. So the Stokes factor associated to a Stokes ray is defined like this. So let me draw the picture. Here's the Stokes rays. Here's a particular Stokes ray. I take two non-Stokes rays, which are perturbations of it. So then I get some canonical solution in this half plane and a canonical solution in the other half plane, and then I can compare them on the overlap. Okay, and since they're both solutions to the same differential equation, they're going to differ by some constant matrix. And that constant matrix is the Stokes factor associated to this ray. And it's somehow important that this is not an arbitrary element of the group G. It's, I mean, in the generic case, these Stokes rays are indexed by the roots of the Lie algebra. And basically this Stokes factor has to live in the exponential of that, of the corresponding root space. But in general, these rays could have collided. So then there could be several roots living on a particular ray, and so then you get a slightly larger part of the Lie algebra here. But anyway, they're unipotent and they're exponentials of parts of the Lie algebra. Okay. And I suppose it's worth noting that there is the same amount of data in the matrix V, because it was an arbitrary off-diagonal element, as there is in all the Stokes data, because you just have a piece for each, you know, each root just appears once here. Okay, I'm not explaining that very well. But that's relevant because to this business about isomonodromy, because what this is about is that we now want to consider the situation where we vary this leading term u, and we ask that the second term varies in some way so that the Stokes data is constant. Okay, so the usual situation for isomonodromy is that you consider an equation with regular singularities at certain points in the plane. And then what you want to do is move the positions of those points, keeping the monodromy around those points constant. Okay, so that's an isomonodromic deformation. In the context of these equations with a higher order pole, it's not enough to just think about monodromy. You should think also about the Stokes data as I've just defined it. And now you can think about trying to vary the matrix U. That's the analog of varying the positions of the poles. And you want to vary V so that the Stokes data is constant. And it turns out you can do that. And you know, there's locally a unique way to vary V so that that happens. And there is a PDE describing that variation, and this is it. So again, if we were in the slightly more classical case where we were varying the positions of the regular singularities, these equations would be something called the Schlesinger equations, which I find very hard to say. But this is the kind of irregular version of the Schlesinger equations. Okay. And you know, these crop up very fundamentally in the theory, in Dubrovin's work on semi-simple Frobenius manifolds. And essentially, if you have a solution to this equation, then you can write down a semi-simple Frobenius manifold. Okay, how are we doing for time? So, but again, so my definition of isomonodromy here, I said that the Stokes factors should remain constant. That's actually not quite a kind of correct thing to say, because as I remember that the Stokes rays are given by the differences of eigenvalues of this matrix U. So if I vary U, then these rays will collide. Okay, so then what does it mean for the Stokes factors to remain constant? So the correct way of saying it is precisely the same form as that as the wall crossing formula in DT theory, and this is somehow the point. So the correct way of saying this is that you should allow these Stokes, you know, you're going to vary this U. These red rays are spanned by the differences of the eigenvalues of U. So these red rays are moving around, but you should allow them to cross. But the correct, and therefore you shouldn't just say that the Stokes factors are constant. What you should say is that the product in the clockwise order of these Stokes factors should remain constant. Because, and why is that the right thing? Because remember, there is some canonical solution to the differential equation associated to a non-Stokes ray in the corresponding half plane. And so again, there's another nice canonical solution associated to this ray. And if you compare those two things, of course, you will just, the change will just be the product of the Stokes factors associated to these three things. Because when you cross a Stokes ray, the canonical solution changes by that Stokes factor. So this clockwise product is a perfectly reasonable thing to consider. And that's the thing that you should think is constant, providing none of the Stokes rays cross this blue line. So this is the correct way of saying the isomonodromy condition. And of course, you see now that it's exactly the same as the form of the wall crossing formula. All that's happened is that we're working in a different group G. Okay. So the idea is that this most fundamental fact about DT invariants tells you that you should be thinking of them in terms of defining Stokes data. Okay. So if we follow that thought, then we should, we're thinking about some CY3 triangulated category. We should not think about GLN anymore. We should think about the group of automorphisms of that torus, since that's where the things living on the rays were. And then we should say that what we have is some kind of isomonodromic family of differential equations. It doesn't really make sense to say that anymore. So we should say meromorphic connections on the trivial G bundle over P1. So epsilon is my coordinate on P1. And they're of exactly the same form that we discussed, we had a moment ago, where, this should live in the Cartan. That was what was U before. And this thing should be in the off diagonal. So that means that, Z should be some invariant vector field. But we discussed that invariant vector fields are just maps from gamma to C, because that's the tangent space to the torus at the identity. So the central charge is a perfect thing to put there. And indeed, it's the right thing to put there, because remember, the rays you're supposed to get by pairing this element with the roots. And that's perfect, because the rays in the DT story were Z of gamma, spanned by Z of gamma. And here we must put some function. And, we don't know what that function is. The whole point is it's being kind of implicitly defined. It's whatever you have to put the thing there that gives you the right Stokes data. So basically, what you're ending up with here are some holomorphic functions on the space of stability conditions, which are defining the Fourier coefficients of this function on the torus. Okay. So that's that's what we get. And this basically, I don't want to say too much about this, but Dominic managed to construct these functions, or at least write down some sort of formal expressions for these functions, more or less by hand, just on the basis that he knew the DT invariants were discontinuous. They had this wall crossing behavior, and he just tried to write down combinations of them and certain analytic functions to try and cook up some functions some objects which would vary holomorphically. And he made them a remarkable discovery that if you do that, you end up, there's a kind of canonical way of doing it, and you end up with some functions which satisfy a PDE. And of course, that PDE was actually the isomonodromy thing. So that's sort of where I came in and did some work with Valerio Toledano Laredo on this. Okay, so I think I'm nearly out of time, so this will be my last slide. So we had this isomonodromy partial differential equation back here. So all we've done is change the group G. So we should write just the same equation down, and we will get something that these F gammas satisfy. So what happens is you get this. So all I've done here is I've written down the particular form of the Lie bracket in this Lie algebra of vector fields. Okay, so you get some PDE, and I just want to re-express this. So I define this function, which is basically what Dominic wrote down. So I take these Fourier coefficients and I put them in a combination and therefore make a function on the tangent space to the space of stability conditions. So these things, F gammas, just depended on a stability condition. But this thing is a function on the tangent space. So remember, yeah, I mean, so what is the tangent space to space of stability conditions at any point? Well, this thing was locally isomorphic to a vector space. So that's easy to work out. They're just deformations of the central charge. So maps from gamma to C. So that's what that theta is. So I can form this combination. And the reason I do that is then that this differential equation becomes a slightly different PDE, which is already known in the literature somehow. That's the point. So I've taken coordinates here. I've just taken some basis for my lattice gamma. So then I have these central charge coordinates, z of gamma I, and I have coordinates on the tangent fibers, which are these theta I. And then you can easily see that this equation becomes this one. And so Ian Strawn wrote to me, I put this in my paper, and then Ian Strawn wrote to me and explained that this is a very well-known equation. It's called Plebanski's second heavenly equation. And it goes back to 1975. And it basically describes the existence of certain complex hyperKähler metrics. So this is where you first see the connection with complex hyperKähler geometry, which is where I will start next time. So you know, it's been a long road, and I hope you've followed it. But so just to quickly recap, what we found was that DT invariants have some particular wall crossing behavior, which makes them look like Stokes data for some family of connections. And if you take that seriously, you're led to write down this family of connections. So, you know, this is the abstract thing which enables you to view DT invariants as Stokes data. And if you do that, you're somehow magically led to this PDE, which describes hyperKähler geometry. So, you know, we'll start again next time with, you know, trying to describe the geometry of what this equation, what is the geometry behind this equation? And there won't be any DT theory or stability conditions next time, I think. So if you're feeling lost, you could at least try coming along to the next one. But I'll stop there. Thank you.
So, Robert, perhaps we could be allowed to start video again. So, are there any questions?
Is there an analog of the second heavenly equation for Frobenius manifolds?
That would, I think, that would just, yeah, that's a good question. So let me see. So that would be, I mean, of course, the second heavenly equation there, I've really got just from this isomonodromy equation by a fairly trivial kind of redefinition. And your question is a good one, and I don't quite know the answer, I'm afraid. You see, I mean, it won't be for a single function. That's the thing, because the fact that we ended up with a single function here is because it's to do with the particular Lie algebra we were considering, which was namely, vector fields on the torus. So, things ended up being described by just a function, a Hamiltonian generating function for one of these vector fields. Whereas this one here, in the case of Frobenius manifolds, the relevant Lie algebra is GLN, and so you can't escape that. There will be some matrices knocking around. So, I think you'll end up writing down some. I mean, what you would basically want to consider is the sum of V gamma over U of gamma. So you would consider that would be some matrix, and it would satisfy some PDE, which was just derived from this one. And I can't think for the moment exactly what that would be, but
the point is, you don't get the massive simplification that you perhaps do here.
Yeah, you don't get something described by a single function. So yeah.
Thank you.
Thanks.
Could I ask something?
Yes, please.
Go ahead. Should I think of this hyperKähler manifold? I mean, it's a bit more physics-oriented question. Sorry. Is that supposed to be the hypermultiplet moduli space?
I don't believe so. No, but I mean, I'm not very well qualified to answer these questions. But as far as I understand, there is. Or at least I don't think so. I mean, because, sorry, maybe you're right.
Bobby, wouldn't that have a quaternionic structure?
Yeah, but you can take the hyperKähler limit of the quaternionic Kähler.
I thought you were going to say you could take the Swan space, but okay.
You can also do that, yeah.
I mean, the difference is that he's fixed a holomorphic 3 form. So if we also allow the holomorphic 3 form to vary, I think we would get the quaternionic space.
I mean, maybe we can answer this question by thinking what we would get in this case of theories of class S, right? So I'm going to get this space of quadratic differentials, and then I'm going to take the tangent bundle for that, or the cotangent bundle. It doesn't really matter, and that's going to be the total space of my complex hyperKähler manifold. Whereas, what would the hypermultiplet? I mean, I know the Coulomb branch would be fixed. You fix the Riemann surface and take quadratic differentials on that. I'm not sure what the hypermultiplet space is in that case.
Bobby, I mean, isn't your question more about supergravity?
Yeah.
So I think there's an important difference here, which is there's sort of two kinds of physics theories. There's one called field theory and one called gravity. And in Calabi-Yau compactifications of, I mean, maybe if you applied what Tom was saying to derived category of Calabi-Yau threefolds, it would have something to do with the hypermultiplet space. But if you applied to the quadratic differentials case, it's a good question. I don't really know what it would be. I don't think it's not what physicists would call the Higgs branch of vacua, which is another hyperKähler manifold.
Mm-hmm.
But I don't see any connection to that. While we're on that topic, for physicists, there's a huge difference between the behavior of the Donaldson-Thomas invariants, or rather the omega of gammas, in these two cases, field theory and gravity, and it has to do with their growth.
Mm-hmm.
So imagine you put some kind of norm, and it shouldn't really matter what kind of norm you put on capital gamma. Then in the gravity case, the omega of gamma, well, the logarithm of omega of gamma, roughly speaking, grows like gamma squared as little gamma becomes large. And in field theory, the growth is much smaller. And this has a big impact on making sense of those infinite products that you were alluding to. So,
yeah, I mean, that's certainly an issue that we would worry about. I mean, of course, the wall crossing formula is the same. And so at least morally, the story, the analogy I'm making with Stokes' behavior seems kind of sound, but it's no good, I suppose, if nothing converges, which I suppose is possible. I mean, of course, we also see this. I mean, and I suppose the cases where I've managed to do any calculations at all don't suffer from this problem. I mean, they're cases where the DT invariants don't grow fast. I suppose the first sort of case where we might start seeing this problem, I think, would already count would be local P2, something like that, right? So I think that's one of the simpler examples where the DT invariants grow very fast along the rays.
They'll grow fast, but not with this kind of so-called black hole growth, exponential of gamma squared, constant squared. So in field theory, you can get exponential growth, but it'll be a smaller power of gamma. And so, for example, I believe the Riemann-Hilbert problem will probably, the integral solutions to the Riemann-Hilbert problem will probably converge when it's less than exponential of gamma squared. But when it's in the supergravity case, I mean, for example, Boris Pielin has written papers about this. It's an important problem that that growth, even for a physicist, makes these products and these Riemann-Hilbert problems problematic.
Yeah, Greg, I think one of the issues is that all of his examples in the Calabi-Yau case are non-compact. They're just neighborhoods of some smaller compact guy. And for that reason, the gravity is not going to play a role.
Absolutely, absolutely. So you're not going to have this, let me call it black hole growth. Black hole growth means that with some reasonable norm on capital gamma, the logarithm of omega gamma as you go along a ray in the lattice grows like quadratically. But as David said, if you're in these non-compact Calabi-Yaus, really that's geometric engineering. It's really more in the field theory setting. And then the growth will be subquadratic.
Yeah, I mean, basically these are issues that we're not bumping into yet because we barely know how to deal with stability conditions on compact CY3 folds, let alone compute their DT invariants, let alone solve the Riemann-Hilbert problem.
Okay, well, but the physicists have an interesting prediction, which is as soon as you make that Calabi-Yau compact, you're going to have this very serious growth condition to worry about.
Yeah, I mean, just while I've got you here then, I mean, I remember reading or hearing a talk of Clay Cordova where he was talking about this sort of thing, and where I got the impression that refined DT invariants maybe helped with this. Is that true? Because you look in powers of the Q, the refinement variable, and don't go order by order in that. Do you know anything? Does that sound familiar?
I don't want to say something wrong. So yeah, I'm not sure if refinement would help. Certainly sum over the spins, the sum over the refinement will have to do with spin quantum numbers. And if you sum over the spins, you're going to have to recover that quadratic. But it could be that there's a very large range of spins. So, yeah.
Okay. But anyway, I completely agree that, yeah. So, I mean, and what's the conclusion? Isn't the conclusion that you don't look for a hyperKähler structure anymore? You look for a quaternionic Kähler or something?
Well, I think as Dave and Bobby just said, yes, it should be quaternionic Kähler, but you can, by maneuvers, you can replace that by a hyperKähler geometry, like the Swan space.
Any more questions? If not, then let's thank Tom again. So we'll take a break now until, well, for an hour and a quarter until 8 p.m. UK time, or